Hello and welcome back. Today we are going to explain the actual mating envelope. The actual mating envelope, or AME, is a concept used to represent the perfect feature counterpart of a real feature, generated based on the actual size and form of the part. This envelope is created by a perfect geometric shape that just contacts the highest points of the feature surface. Let us first consider an external feature of size. In this example, we have a pin with a size range of 14.6mm to 14.0mm. The actual mating envelope, in this case, is the smallest perfect feature counterpart that can be circumscribed about the external feature. In simpler terms, we imagine a perfect cylindrical gauge. This gauge is the smallest possible size. It just touches the highest points of the pin surface. Even though the real surface may have irregularities or waviness, the AME forms a perfect boundary that encloses the feature by contacting only the high points. For this part, the actual mating envelope is generated at the smallest size that still fully encloses the external feature. This envelope acts like the inspection gauge used to check whether the part will clear during assembly. For example, the actual mating envelope for this part is 14.58mm. This value represents the smallest perfect cylinder that can be placed around the pin while touching its highest points. Although the local actual sizes of the part may be smaller than 14.58mm at different locations, the overall boundary created by the high points defines the AME. Since all local sizes lie within the 14.58mm boundary, the part satisfies the actual mating envelope condition. In another case, the pin shows a bow or curvature. Here, the actual mating envelope is 14.5mm, even if the actual local sizes may be as low as 14.2mm. Even with this bow, the AME still forms a perfect cylindrical boundary at 14.5mm. Since all actual surface points lie within this boundary, the part passes inspection and can be assembled. Now let's look at an internal feature of size, such as a hole. For internal features, the actual mating envelope is the largest perfect feature counterpart. This envelope represents a perfect pin or shaft that would fit into the hole. For this internal feature, the actual mating envelope is 14.1mm. The hole must be equal to or larger than 14.1mm. If the measured hole size is 14.4mm and the smallest local size measured inside the hole is 14.1mm, then the actual mating envelope condition is satisfied. The part will accept the mating pin, even when there is axis tilt or form deviation. The condition is still met as long as the actual hole sizes remain larger than the AME. Now let's move to a more realistic example. Here we have a projection with a 34mm diameter, including size tolerance, an orientation tolerance of 0.05 relative to datum A. Datum A is the flat base surface, and the vertical pillar acts as datum B. Additionally, the pillar has a 10mm hole with a size tolerance of plus or minus 0.25mm. A position tolerance of 0.5 at MMC is applied relative to datums A and B. First, the datum feature A is established. Although the surface is not perfectly flat in reality, a perfect datum plane is generated by contacting the high points of the surface. This plane represents the true geometric counterpart of datum A. Due to manufacturing variation, the axis of the feature may be tilted. This tilt must be controlled within the orientation tolerance of 0.05. Now we introduce two important concepts. First, the related actual mating envelope, RAME. This is the perfect feature boundary. It is generated using datum references. It represents the ideal location and orientation of the feature. And second, the unrelated actual mating envelope, UAME. This represents the real feature, including tilt, form error, and manufacturing deviations. During inspection, the axis of the unrelated AME must lie within the tolerance zone. Specifically, it must stay inside the 0.05 perpendicularity tolerance zone relative to datum A when inspecting. The external feature. The unrelated AME must fit within the boundary of the related AME. This boundary is defined by size tolerance, 10 plus or minus 0.25, position tolerance, 0.5 at MMC, and the orientation constraints. If the unrelated AME stays inside this boundary, the part meets all functional requirements. Understanding AME helps you clearly see the relationship between size, form, orientation, and assembly functionality. I hope this explanation clarifies how AME is generated, how it is inspected, and how related and unrelated AMEs interact.